Welcome to this introductory video on smart data and the use of ontologies, part of the ORION project, which is financed by the European Joint Framework for One Health. Let's start looking at data in a simple tabular format that you may be used to handling every day. So I created here a table, a spreadsheet to enter information about books, and I added the columns that I thought were appropriate for that: author, title, year published, genre. One of the limitations of tabular data is that the tables or the spreadsheets are only useful in one specific context or for a specific object. If I now want to enter information about film, I don't need the column for author. What I actually need is a column for director. And if I want to enter information about people, then I really wanted to have name, not title. Of course, this limitation can be addressed by creating one table for each different type of object, which is what relational databases or Microsoft Access does, for instance. But in this video, we're going to see yet more powerful ways to deal with data. Before that, I just want to point some more limitations that we want to address. Here, this book has two genres, and by entering this information in the same cell, we have lost the ability, for instance, to filter this column based on genre fantasy. And here we have some misinformation that we're not sure is missing, someone forgot to enter, or is not appropriate for a book to have director. We can address all those limitations if we break free from the table and don't try to stay connected to rows and columns at all. We just say whatever we want about whatever things we want, similar to the way we may think in our heads. So Justin Garden wrote the book The Solitary Mystery. The Solitary Mystery has genre fantasy, but also has genre philosophical fiction. I could have started from the book Flowers in the Attic has author V.C. Andrews, and in fact those two relationships, wrote book and has author, for us, they are symmetric. If we know one, we immediately know the other. We know those things, we understand those things. They're obvious to us humans because we understand this thing called a book. We understand what it is, and we understand, for instance, that it's different from the thing called a film. And a film would have other characteristics, such as has director. If we look at the data here and think about the concepts we understand that allow us to understand this data, we see also the concept of a person. And we know how that's different from a book or a film. So let's step back from our data and start thinking about the concepts or the knowledge we have that allows us to understand those data. Let's model this knowledge. So we understand this thing called person, and we understand it must have a date of birth, and it may have a date of death. We understand this thing called a book, and we understand that people and book are related by an authorship relationship. In fact, people can also be related to other people through specific properties, and if we want to start really modeling this knowledge, we can add constraints such as one person can have several children, one child can have only one biological father. But let's stick to our example and the relationships we need to model the data I've shown previously. So we also need this thing called a film, which can be based on a book. A book can also have publication date, and I've been using some conventions here. The circles are data types and the squares are concepts. The arrows are the relationships between those things, between those concepts. And as I said before, you can put specific constraints on these relationships. We can say, for instance, a book can have more than one genre. In fact, here I've modeled it as a book must have at least one, but can have more genres. So we started modeling the data as a graph, and now we are actually modeling knowledge. And whether we noticed or not, the data around us, the way data has been handling around us, has been evolving to more and more be understood through these knowledge models. Allow the computer to see these knowledge models and reason with data the same way that people can. So if you go on Google now and you search for an example, Stephen Hawking, it used to be that in the old days, it used to be that Google was just searching for all documents in the world where these specific words, let's call them a string of letters, appeared. Any document where this string appeared. Now Google understands this is a specific person, that you're searching for a person. The proof of that is that when you search this, on the right side of the screen, you get this that Google calls the knowledge model, which show you things that are only relevant for a person. For instance, what's his profession, what's his date of birth and death. If you had searched for a book, it would have shown you different characteristics which are more relevant to a book. So Google is understanding this not as a string, but as a thing, as this type of thing called a person. And it's also understanding much the same as in our knowledge model that we've shown before. And it's also understanding relationships between people. As you can see here, Jenny Hawking is a former spouse of Stephen Hawking. Another proof that Google can understand characteristics or relationships related to things is that you can, for instance, search for properties. How tall is the London Shard? So it understands London Shard to be a building and to have this property of height. So we're going to talk about smart data and what smart data can do through this narrative called Clever Things Google Can Do. We're going to use them as an example to show you what smart data can do. We already talked about seeing things, not strings, and understanding properties so that you can search conversationally. For instance, how tall is this beauty? When did this president start his or her term? The third thing I want to talk about that is key to why we want to use smart data is interoperability, the ability of the same data to be understood by different computer systems or different softwares, different programs. The example we use is, for instance, when you receive an email with a flight reservation, Google Calendar adds that to your calendar automatically. So both your email and your calendar are understanding that same piece of data. To exemplify how that can be, how that works, we're just going to go back to our data and look at how we're storing the data. So we started with a tabular format and then we moved to the graph because the graph allowed us to be flexible. But what we ended up was modeling not just the data, but modeling also the knowledge behind those data. So if you look at the first row there of our Excel, that whole first row there is about this book called The Solitary Mystery. And when we model the knowledge, we model the thing called the book. So we know The Solitary Mystery is a book. So the first thing we do is understand all the concepts in our data. So Justin Garden is a person, fantasy is a book genre, philosophical fiction is also a book genre. So now we can start entering information about that book. And what we'll do is, for what you used to see as each individual cell in your table, in your Excel, we're going to make a statement. So those are independent statements. I'm not constrained by how many columns I left for each characteristics. I'm just going to enter every piece of information independently as its own statement. So let's follow the first row there and say everything we want to say about that book. The Solitary Mystery has author Justin Gardner. The Solitary Mystery was written on year 1990. The Solitary Mystery has genre fantasy, but here I'll make two statements. The Solitary Mystery has genre philosophical fiction also. So I can make many statements about genre because my model allows me to do so. And every statement has the exact same structure of three pieces. So we're going to call each of those statements a triple. It has a subject. In all those statements, the subject is the Solitary Mystery. Then it has a verb or a predicate or a relationship, has genre, and then it has a subject, fantasy. So the thing I want to say something about, the characteristic I want to state about it, and then what is my actual data, what would traditionally go in my Excel cell. So I've broken free from the table and I now have independent statements, and this is what now I'm going to call my data. And those data can only be interpreted if I have the key to understand those data, the model that tells me what are the concepts in those data and what are the relationships between them. And much the same way we translated our graphical data into those statements, we can translate the model we've built to how we understand the data, the model of the concepts, into this ontology. Together, the data and the ontology are called a knowledge model. The main thing to notice here, though, is that now the key to understand the data, we're not trusting it lives in people's heads. We're not trusting people just know or understand my columns. We explicitly model the knowledge needed to interpret those data. We make explicit statements that are needed to understand those data. And better yet, because those statements are coded, they are entered as a computer knowledge as a model. The, those explicit assumptions about how you understand the data are not just understandable by humans, but also by computers. So we can formally define an ontology as a common vocabulary to share information, which is machine interpretable, which is understandable by computers. So now we're not just talking about data, we're talking about flexible way to store the data, data that we have an agreed upon model to understand. Humans can refer to that model, but computers can also understand that model. This is how, for instance, Google understood Stephen Hawking to be a person. It's referring to an ontology, in this case an ontology called schema.org, which is an ontology that has modeled common things in the world. You see the things that schema.org has modeled on this slide to the right. So person, organization, place. This ontology has this key to understand data that has been tagged according to these different types. So when you search for Stephen Hawking, Google looks for Stephen Hawking and finds it as a person and is able to give you specific things about that person. In the same way, schema.org has a specific class or specific type of thing called an event. When you search on Expedia for a flight, Expedia looks all over the world on all flight companies' websites and returns to you all those results. Yet none of those companies have not made data sharing agreements or set together to define exactly in which format they were going to share their data. What happens is they are all adhering to these, they are all putting their data into the same format following the same key, which in this case is schema.org. So when they store data in their website, they store data in the format compliant with that key, and that key lives out in the web. So any program, any software can refer to where the key lives, fetch the key, and translate, understand, decode their data. So when they publish their data, any of those flight companies, they say this data has context and then puts the address, the web address for where the key lives. In this case, the key is an ontology called schema.org. And then they say, following this key, I'm now going to enter my information, my data. I have data about a thing of type flight reservation, and then they can enter data about that flight reservation. I'm going to enter data about a thing of type flight. According to the key, a flight can have a flight number, so I will give the flight number for this flight to be, for instance, 110, and so on. I can give now information about something of type airline. In this case, the airline is United. I'm going to enter information about a thing of type airport. In this case, the San Francisco airport. So they publish data which follows a key, and the key just lives out there in the web. It's time to review some of the concepts. So some I have talked on this video, some you will find, you hear, you may have already heard, you hear when you're researching the subject. So it's good to clear those concepts so that you understand what they mean when they come about. Resource Description Framework, or RDF, is the data interchange format that allows us to see data in the format I've been talking about in this video, in the format of triples, subject, predicate, and object. So when we're thinking of storing data in this way, when we're talking about flight companies publishing their data in this way, we're talking about RDF data. The key to understand those data lives in an ontology, as we talked about before. And we started drawing our knowledge model, or the knowledge we needed to understand the data, as boxes and arrows. So we're going to now call them formally as the concepts in our ontology and the relationships between them. Or you may also see those things called the classes and the properties. They mean the same thing, concepts and relationships, or classes and properties between those classes. And an ontology is coded, written into a machine interpretable format using this language called OWL, Web Ontology Language. So it's spelled backwards there. Because we're modeling not just the concepts but also the relationships between them, we are using semantics. So you may also see this word used. You may also see people referring to this as semantic tools. We've talked about schema.org, which is ontology for general things in the Word. You may also want to check Bioportal or the Open Biomedical Ontologies Foundry, which have lists of ontologies specific for the biomedical domain. To close up this video, we're just going to summarize what are the advantages of storing data in a smart way, what's the advantage of moving to this smart format for data. The first one is that we harmonize the way we share data, not just for common understanding among people, but also between programs, software. We saw it was a flexible format to store data, but more importantly, we make all assumptions we need to understand the data explicit. And because we put these explicit statements into a model that the computer can understand, then the computer can reason about data in the same way people can. And in the next video, we're gonna see how the power this gives us to automate some of the steps of handling with data. Instead of having people manually handling data, we can let the computer do a lot more now that the computer understands the data and the relationships between different pieces of our data. One thing I haven't explicitly shown is that when we code a knowledge model into an ontology, that model can always be reused. So anyone can borrow our codes and build on top of them. We talked, for instance, about people only as authors of books. Someone could get our codes and made more explicit statements about people, what they are, how they relate to other things. They could now enter the concept of a car and how people drive cars or how people make cars. So every piece of knowledge coded as an ontology is reusable, and that means that every time we start a new project or we start building something new based on ontologies, we don't need to start from scratch. We can just reuse all the knowledge already out there in the world coded in ontologies. And as knowledge evolves, as it always does, we can also review our ontology and review the assumptions we have made, while we still holding the power to understand past data. If you want to read more about this subject, you can refer to Data-Driven